Our team's project was 3D printing of a biocomposite slurry using direct ink writing. This project is sponsored by the Convergence Center for Living Multifunctional Material Systems and is comprised of 5 students from Penn State's College of Engineering.
Direct ink writing is an additive manufacturing process based on extruding shear thinning ink. It is a low-cost option for manufacturing heat-sensitive, organic, and biocomposite polymers. The development of biopolymer inks is critical for several fields, such as the food, cosmetics, and medical industries. Unfortunately, commercial bioprinters lack the extensive user control and open-source nature suitable for academic research and further development of this technology.
The overall objective of this project was to develop a biocompatible slurry that could be successfully 3D printed through the use of a customized direct ink writing printer attachment. These 2 design components were prototyped in parallel, with half of the team dedicated to the printer attachment and the other half focused on the slurry development. Next, Zach will be describing more details about the printer attachment design.
For the prototyping process of our printer attachment, we had 3 main designs that we went through. The first one being made mainly on estimations of measurements. The second one, once we got our parts that we needed, such as our stepper motor and wires, we were able to make better adjustments to the dimensions that we needed, such as height and depth. And then our third one was really the optimization of the printing process, 3D printing, strength, reliability of the part, really making it as sturdy as possible. The overarching design is basically just a stepper motor, which is in the centerpiece of the printer, which moves up and down along guide rods after it's being driven, and that allows the syringe to print the slurry that we're designing.
Once we had our final design printed and assembled, our next step was to program the motor's movements and to attach the assembly to the printer. I hooked our stepper motor up to an Arduino board, which allowed me to control its movements using small scripts on my computer. Once we had the part attached to the printer and had control over the motor, it was time to put in some slurries and start testing.
When it came to actually printing the slurries through the printer, slurries at 5, 10, and 15 weight % ethyl cellulose were used. When printing these, we were looking for how easily they printed from the syringe and how well they kept their shape. These were printed in an S-like pattern, and pictures were taken over a span of 30 minutes to see the spread over time.
Moving forward, our team is handing off the prototype and the documentation to our sponsor, Dr. Basak. She will then be sponsoring another capstone group next semester that will pick up where we left off and continue the work that we've done. Since I had the most hands-on interaction with the prototype, I'm actually going to be sticking around to help get the next semester's group up to speed. They're most likely going to be doing future work with the ethyl cellulose ink slurries, such as looking at different synthesis techniques, looking at different rheological measurements, as well as different post-processing methods for the as-printed ink.